Hello, everyone. Welcome to the second MultiScale Talk given by Dr. Antoine Barbot. Antoine is a senior researcher at FemtoST Institute in Besançon, in France. He has obtained his PhD degree in microrobotics from C2N CNRS in Paris. And he had a 3-year-long postdoctoral stay at Imperial College in London. So today, Antoine is going to talk about how to design compact microactuators. So Antoine, please go forward and rock and roll.
Thank you very much, Zoran, for the introduction. So let me start sharing my screen first. So let's start with this. So can you see my screen all right?
Yep, pretty clear.
Perfect. And so also, sorry for the delay, let me sure I check the timing so I don't spend too much time speaking on this. So yeah, thank you again. So what I want to present today is how to design compact microactuators, and especially my interest is to focus on the use of surface tension. So here you can see a small bug trap in a drop of water, just to remember that surface tension is quite a huge thing at microscale. And I will present how I use it for two applications. One, the design of a micro piston at the tip of a capillary, and the other one to deliver and sample a small quantity of liquid, so to our drug delivery and liquid biopsy. So this work has been mainly done in Imperial College in London, and I'm continuing this in FemtoST here in Besançon. So first, let's start with the motivation. What is so interesting in designing small actuators? And so what we want to have is small enough actuators and sensors so we can embed them at the tip of a long tube or a fiber, if you prefer, so we can access confined microenvironment. So this would be useful for microsurgery application to reach deep region of some organism, or as a biology tool to have single cell manipulation, or to get a tool inside a microfluidic chip. Also, it could be useful in microfabrication because it's always nice to have tools that have a small footprint. However, as we scale down, the challenge is really to get powerful actuation on such small footprint. So to get a good understanding on this, and to understand the difficulty, it's really important to focus on scaling effects. So here I put different objects of the normal life, I will say, on this scale. So on the x-axis, you see the scale, on the y, it's the power. So they are all systems that part of the system is generating some power. And we can see that as we scale up, the power increase not linearly, but more or less following a trend, a cubic trend. So it's a scale log here. So if we see a power plant is like around it's 100 meters, so it's way it's 100 meters, it's 100 times bigger than a human in scale, but it can produce much more energy. So this, what's the conclusion of this is that power roughly scale with volume, and it's a really good news for scaling up. So as I say, if we take this human, we have like a 3/4 of the mass roughly, which is dedicated to power generation. But as we scale up, so here as an example, I took the electric power generation in France, and it's only a part of the power need, but it's quite a significant part, and it's only 0.005% of the surface, which is a good news, because if it was 3/4 of the space, it will be awful to live anywhere, because everything will be occupied by power plants. So scaling up is really good for power generation, which means scaling down is really tricky, because now as we scale down, the volume we need dedicated to power generation become quite big. So here are a few examples. On the left, I will start with a magnetic gripper. So it's The scale is here, so it's around 1 centimeter, and we can see there is a lot of the volume, even like most of it, which is dedicated to converting the electricity into force, so the gripper can grasp and even cut a small tissue. So it's really an interesting work. However, it's hard to just take the same design and scale down furthermore. There is few different mechanisms, some based on polymer actuation and or optical tweezer that scale down, so they are both like at the tip of an optical tweezer and they are both gripper. However, the force generated by the system is quite low. So in this case, enough only to grasp something, but we cannot cut anything. So it's not so interesting for surgery application, for example. So here I try to display really where is the difficult region and what is what we aim. So we aim for really compact actuator, which means we want to have a characterized size which is roughly the same order of magnitude than the displacement. So of course we have like tools like AFM and FIB that allow displacement even at the atom scale, but their size is more or less the size of the table. So it's really hard to have something compact, and even MEMS actuator have a really relatively large footprint compared to the actuations they can give. So to succeed this and to have like high force on this actuator, it's important again to come back to scaling low, and to I think it's important to take like physics effects that are quite important at low scale. And it's particularly the case of surface tension and pressure, that because pressure has a square dependency with the dimension and surface tension a linear dependency, they scale like really nicely and become predominant at the micro scale. So on this talk, I will first present one example where I use pneumatic force for a piston, and I also use a bit surface tension, to be honest. And after, how I focus on only surface tension to design a tool, a compact tool for handling a small quantity of liquid. So first, let's focus on the pneumatic approach. So as I say, pneumatic is quite interesting because we can have large force at this scale, and also it's easy to connect to a capillary, which is a bit a trivial argument, but on the engineering side is quite interesting. And the main challenge on designing a small pneumatic actuator, so small piston, is really to deal with the seal. So if the seal is the black rubber parts that you have in for example, in a syringe that you could use in a lab. And because this seal have a lot of friction with the cylinder to make good sealing, it doesn't scale down nicely, because as it scales down, the friction also becomes really important. And so the actuation will be highly nonlinear and also highly impacted by this friction. So the alternative approach that we use here was to use a liquid sealing. And so for this, we use a capillary effect, and we are all familiar with the capillary effect, where water like fill, if there is a small opening, water will fill it. Like if you have a capillary tube, water will fill it, will like to fill it. So here it's a bit the reverse problem. If the water fill a small region, it will be really hard to push it away with gas. So it means that if we have a water seal like this, it can withstand some pressure difference. So it's really good to make this piston. It's already have been used at millimetric size, and it has been also shown on 2D, but here we wanted to show it at the micrometric size and on 3D designs that could be that could look forward this surgery application. So what we did is we print this piston with a 2-photon polymerization. So we use the commercial machine Nanoscribe, and it's a great tool because we can design almost any shape we want. And so we print the cylinder and the piston, and we directly print it on the capillary tube. So now we put the small liquid as a sealing. So we put some oil so it don't evaporate, and we can actuate it. As you can see here, we can push it back and forth. So it's let me display a video. Here is the actuation of the piston in real time at 1 Hertz, and we can see the liquid sealing. So this work has been published in Science Advances. And of course, as I say, what we are interested in is not only the piston, but it's to deliver an important force. And so to check this, we put a force sensor, and we had like quite important force, around 100 of micronewton, which were way better compared to the footprint to the MEM solution. So we were quite happy with this. And here it's maybe some characterization. It's not the most interesting part is probably what is shown here, where you have the force on one side and on the pressure. And what we can see, it's what's happening here is that the sealing made by the oil, or liquid sealing, is breaking, and so some gas can pass through. And what I've found really interesting is that it can still like withstand some pressure. Of course, there is leakage, so it's not an interesting solution. But as soon as we come back under this critical pressure, the seal can recover its original shape, and we can actuate it as nothing happened. So in a way, a liquid surface is, as we all know, it's some sort of self-healing material, because you can like deform as much as you want surface of a glass of water. After at the end, it will remain the same surface. So I find it's an interesting thing to keep in mind. So to conclude briefly, the gap of this piston was around 3.5 micron. And so by decreasing this gap, we could aim for higher pressure. So right now we are around 0.1 bar, but we could really go for higher pressure and so higher force on this piston. Of course, a piston in itself is useless. So what we did at the end was to design small compliance gripper, so we could demonstrate like a manipulation task. So here is a video. We have this gripper, and it's at the end of our glass capillary. So what's really nice is after the capillary can be bent in any direction, it's quite flexible. And after, with the pressure, we actuate this gripper and make this pick and place operation of a bit. So I really love to make this experiment. It's like a small funfair challenge, but we're also quite happy with this result. As I said, so this was the region we aim for. So here we are more or less here. So it's quite nice for us, because we had like a system with dimension roughly of 100 micrometer and a displacement of 30 to 40 micrometer. And we could improve this with the design. So it was a good first proof of concept that it's possible to go in this region. And now we want to focus to develop a bit more to get high force, and maybe to succeed to cut with this small gripper some tissue. But as you saw, one interesting thing in this pneumatic actuator was to play with the surface tension between the liquid and gas. And so now I want to focus on how we could use this for liquid manipulation. So just to come back on this scaling law and to make some pictorial elements which make it easier to grasp the phenomena. As we reduce the scale, like the surface energy really become predominant. And if you see at raw scale, like a wave crashing on the shore, it will disperse in many, many drops. But if you look at the drop from a faucet that impact like some plates, it's more or less maintained in one drop. There's few splashes. And if we scale down even more, here it's like a drop that it's bounce in every direction, and it stays as one drop. So it's really important that to keep in mind that droplet creation at small scale, it's really take a lot of energy compared to the energy of the system. So of course, some people have used this fact, and here is example of works that I really love. So some people use Droplet to fold some elements. So here it's a liquid metal to make a small rotating motors. Also to displace, to pick and place element just by a drop, and of course something people are maybe more familiar with to make to generate drop in microfluidic system with water and oil emulsion. So again, in the idea of designing these compact actuators to go at the tip of long tube for surgery, we're wondering how we could use this to make a local drug delivery and also local biopsy. So the main problem is why we can't use a classical catheter, like even a small one, which could be just a plain tube, a plain capillary tubing, so maybe 100 or 200 micrometer. Well, there is a lot of dead volume, and if you want to sample something, the useful volume is really small. And also, if you bend this tube, it's really hard to control how much you deliver just by controlling the amount you push at the back. So the solution we investigate was to use a droplet of water and to push it by the gas. And so there is a few challenges for this. The first one was to create a repeatable droplet. Second one, to transport it, and finally to deliver it. So let's look quickly at this different challenge. So the first, for the droplet creation, we use the capillary valve mechanism, which is well known in microfluidic when filling microfluidic ship. And basically the same principle than I use with the piston. If it's that small region, if they are hydrophilic, they prefer to be filled with liquids and gas. So it means it can withstand some pressure difference. And so by putting a small passive valve in our tube, so this passive valve was designed by the nanoscribe, it was possible to first fill the tube and then remove the water and get a droplet stopped by this passive valve, and to keep it in a repeatable fashion in our tube, ready to go and ready to be sent in our capillary tubing. So that's for the droplet creation. The second challenge was the transport, and mainly the thing is that you need a hydrophobic coating, and it's quite obvious if you have a hydrophilic coating, you will just disperse the droplet in the tube. So we learned this the hard way, of course, but we perform a hydrophobic coating on the tube, and we're quite happy on here the experiment on a 20 centimeter tubing, and we could have 10 nanoliter at the creation, and then 10 nanoliter at the back. So it was really nice. And finally, the last interesting point is that we can achieve quite high speed, so it's half a meter per second. Mainly because only the droplet is having some friction with the tube, and not like the full. I mean, compared to a tube that will be with a fully filled with liquid. So that's quite interesting as well. But at the end, we want to deliver the droplet, and again we use a capillary valve mechanism. So for this, we draw like many holes in a structures that connect the inlet and the outlet of our capillary. And so what happened is, because the hole is small enough, the gas cannot escape, even if it's higher pressure. And so when the droplet arrives, it's make a fluidic junction with the environment, if it's liquid, and then we can deliver the drop. Or by playing with the pressure, the droplet can arrive and can trigger a sampling mechanism where we collect small liquid from the environment and we get it back on our system. So here it's an example of the delivery. So we can see the droplet arriving. So the gas is circulating inside the device, and there is no leak of the gas, but the droplet is fully expelled outside. So I've got a quick video as well for this. So here we see the inlet capillary, the outlet capillary, the nanoscribe structure, which is printed at the top, and the drop is expelled, but not the gas. So we are sure we have our exactly 10 nanoliter drop expel. So we are quite happy with this, and we made different characterization. Basically, what to remember is that because we can control a lot in the geometry of this small cap, which is a small microfluidic component, it allows us to make, if we want more, to deliver all the droplets or to sample a precise droplet, we can play on this parameter. So it's really useful toward both application of drug delivery and small liquid biopsy with minimal impact. So it's been published in Advanced Science recently. So this is a full device to finish. So you can see this tubing is really small and could be 2 meters long. It wouldn't be a major problem with the creation, transport, and delivering of the droplet. So just to finish, I wanted to highlight, as you saw, I think like surface tension can be really the base of many actuators at small scale. And something a lot of people know about is the fluid joint. If we have like some element floating on a small drop, you have a lot of degree of freedom here. So what is interesting is how can we make it active? So if we deform the drop, can we control a floating object in 6 degrees of freedom? And I hope this could be used to make really the future of compact, minimally invasive tube. Of course, there is few challenge, but mainly fluid manipulation to deal with contact angle hysteresis is also quite a good challenge, and there is a huge need for rapid modeling, so it can be used in both design and control. So thank you very much for your attention. I want to acknowledge all these people I have the pleasure to work with. Thank you.
Awesome. Very beautiful work. Very beautiful work. Okay, let's go through some. I have some questions now. Yeah. It's time just that you and I can discuss your work, because it's actually it might inspire some other researchers working on this topic, or researchers who are not working on this topic might get also inspired.
I hope.
Yeah. So, for example, when you showed the droplet, how it's getting released from the actuator. Mm-hmm. So is it here this picture? So is it really a droplet, or do you release it like in small satellite droplets like making a form of an aerosol?
No, it's really a droplet, because maybe I went quite fast on here, but outside it's a liquid environment. So basically here it's the liquid is here for the video. I put ink in the water, so we could really see
visualize it,
the droplet in the water. If you wait for a long time, you will see the ink diffuse in the water. So it's really like one phase outside. It's only liquid. So that's this system work well only in liquid, because if you would have gas, it would be the reverse phenomena. So the gas would be able to escape in the environment, but the liquid would be stuck inside the system and will arrive by the input and come back by the output.
And on the picture on the left, why do you have this kind of looking like a perforated membrane, this whole
yes.
So, yeah, why do you have so much this kind of holes?
So basically, it's to make this capillary valve where it's to let the fluid pass, because the fluid can fill it by capillarity, but the gas cannot pass because it needs to deform the interface to pass through these holes. So basically, one hole would be enough, but to make it fast and efficient and also robust to the blockage of one hole, we made many of them. Mm-hmm. So it's why we have a lot of them.
Yeah. So that's sometimes because I have actually very limited experience in microfluidics. Did it happen that you pump too much pressure and then you blow your microfluidic system?
Yeah.
Or some joints here, that they break.
What happened here, if you increase the pressure, is that at some pressure threshold, the gas starts it's enough for the gas to deform and to pass through this small hole. And then you start to deliver the gas, and it's making like tiny gas bubble. So here on the system, the holes are around 8 micrometers, and it's end up the maximum pressure we can put in the system before seeing a leak is around 300 millibar. So so that's it. If with smaller holes, we could go at higher with higher pressure.
Yeah, you know, if you go to slide 16, you just showed that you had just one before. Yeah, so you said that here you have put some hydrophobic coating in the capillary. Well, in the previous talk from Dr. Maja Vučkovac, she actually showed that if you have a super hydrophobic coating in a capillary, the more viscous fluids will flow at a higher speed. Did you know that fact?
I saw her work, and it's really interesting. In fact, sending like a small droplet in a hydrophobic tube or capillary was we didn't expect it, but it was really interesting. So I was really happy to read about this. And as I understand, the main hypothesis is that there is like a slipping on the boundary, and so viscous solid advance more as a plug than this parabolic flow, if I understand correctly or what. And basically, it's I don't know if it's something similar or not, and we didn't focus too much on it in the paper. But here you can see on the dot line is the speed we could expect with this no slip condition.
Yeah.
So of course there is like advancing and receding contact angle, but that makes some hysteresis. But it would suggest that I was thinking that I would have something below, because it's like really her upper limit, and I was really surprised to get something that like a experimental speed that is above this limit. So I think there's quite interesting phenomena happening here about like the droplet slipping on hydrophobic tubing, and especially to make this droplet go faster. It's also something really interesting to look a bit more. I hope I have time to go for this.
Yeah, I actually have only one more question. If you go to slide 15, I think it's the previous slide. Yeah. So what kind of frequencies you can achieve just making these droplets? Like how much from 1 to 4 you can go? How quickly you can go from 1 to 4?
So for now, to be honest, the frequency is I would say 0.001 hertz, or so basically it take me 10 minutes if it's the first one of the day, and maybe 1 minute when I'm used to, because everything was controlled manually. Like this waterfront was with a screw syringe, and so sometimes it need to be really delicate, and the feedback was made optically with a microscope. After there is, but it's a really interesting question, because it could be possible to make it automatic, but it's still what is interesting here. It's you suffer a lot from the hysteresis of the wetting and unwetting condition. So it's not like in a microfluidic ship where you can make a lot like really quickly, like 1,000 per second, a small water drop in a oil solution. Because in this case, in this case, the surface of the microfluidic ship remain in the same condition, is wetted by the oil. Here you have to wet and unwet, so it's harder to find like some sort of natural equilibria. And I think we will need to have some feedback loop and on the pressure controller. So some cameras that detect the front and then that control the syringe really make it robust. So it's why we didn't improve this too much, because it needs some step of automatization. And for now, it's human based. But so to answer quickly to your first question, I think it could be possible to go to 1 Hertz, 2 Hertz, maybe 10. But with this phenomena, it may be tricky to go to thousands of Hertz.
Yeah. Okay. That's it for now. I'm looking forward for some more interesting work coming from your lab, and then that you can give a talk again in a year or a bit distant future. Okay.
Well, thank you very much for the invitation.
Yep, glad to have you.